In this section, we'll be looking at the graphs of polar equations on our polar coordinate system. We'll first begin by plotting points, and then later on we'll look at some techniques to simplify the process. Here our first polar equation that we're going to graph is r is equal to 4 cosine of theta. So we're going to choose values for theta and then calculate r. I've already chosen values of 0, 30, 60, 90, 120, 150, 180, and 210 for theta. So when theta is equal to 0, we know that the cosine of 0 is 0, so this becomes 4 times 0, which gives us 0 here. When theta is equal to 30 degrees, we know the cosine of 30 is the square root of 3 over 2 times 4 will give us approximately 3.5. When theta is equal to 60, the cosine of 60 is 1/2, so 1/2 times 4 will give us 2. 90, cosine of 90 is 0, so 4 times 0 is 0. When it's 120, we know the cosine of 120 is negative 1/2, so negative 1/2 times 4 will give us negative 2. And we can continue like that and complete our table. Now let's look at plotting our points. Our first point is 0, 0, which is at our origin. Then for 30 degrees, which is the same thing as pi over 6, we have 3.5. So 3.5 and pi over 6 is approximately here. When 60 degrees, we have 2. So it's approximately 2. 90 degrees back to 0. When it's 120 degrees, which is 2 pi over 3, our r is negative 2. Remember, r is our directed distance. Since it's negative 2, it's not going in the opposite direction. So even though our angle is here, r is going to be down in this direction. So negative 120 is approximately, negative 2 is going to be approximately here. Similarly, 150 degrees, our directed distance is negative 3.5, so it's going to be negative 3.5 in this direction. And when it's 180 degrees, it's at 4. We can see that if we continue by choosing more degrees, for example 210, here we have 210, we have negative 3.5, will take us back to this point. So by choosing additional points, we're only going to repeat the points we already have. So we could have stopped at 180 degrees. Now if we join our dots to graph or equation, we can see that we get basically what should look like a circle. So this is actually an equation of a circle. So by plotting this rectangle polar equation, we see that we get the graph of a circle. Now from this graph, we can see that it's symmetrical from the polar axis. So we actually only needed a few points above the polar axis to reflect it down. So if we had chosen maybe just the first 3 or 4 points, we could have reflected those points down to give us these two values, so because it's symmetrical around the polar axis. So what we're going to do is actually look at some of the ways of determining symmetry, so to make our graphing a little easier than this. Here we're looking at symmetry with respect to the line theta is equal to pi over 2. So here over line pi over 2, we have a point r theta, which is in our first quadrant. When it's symmetrical to the line pi over 2, it's reflected over in the second quadrant. So here we have the reflected point. The coordinates for a reflected point is r and pi minus theta. If this is theta, then the reflected angle here will be theta. Because all of this is pi and this is theta, then the angle will be pi minus theta. So the r is the same r, and we have pi minus theta. R, the coordinates for the reflected point is negative r, negative theta. Here we have theta, so negative theta would be down here. Remember, r is our directed distance, so if this is negative theta, then negative r means it's being reflected over here. So from here, it goes back to here. So we can see for either of these coordinates, will give us the reflection of r theta around the line theta is equal to pi over 2. So to test for symmetry with respect to the line theta is equal to pi over 2, we replace r theta with negative r negative theta, r with r and pi minus theta. Now in general, the graph of r is equal to some function of sine theta is always going to be symmetrical with the line theta is equal to pi over 2. Now we're looking at symmetry with respect to the polar axis. Here we have our point r theta, which is in our first quadrant. If it's symmetrical with the polar axis, then it's going to be reflected down in quadrant 4. Because this is angle theta, this angle here will be negative theta. So our new coordinates, or the coordinates for the reflected point, would be r and negative theta. Or it could be negative r and pi minus theta. Because if we reflect this point around here, this would be theta, the equivalent of theta. Then this angle here would be pi minus theta. So this is our angle, and if we change the direction of r, then it comes back down here. So this would be pi minus theta and r, but negative r would move it back down here. So here we have two alternatives for the coordinates of the reflected point around the polar axis for r and theta. So to test for symmetry with respect to the polar axis, we're going to replace r theta with either of these. So with r and negative theta, r with negative r, and pi minus theta. In general, the graph of r is equal to some function of cosine theta will be symmetrical around the polar axis. Here we're testing symmetry with respect to our pole, or the origin. We have our point r theta, which is in our first quadrant. And if it's reflected around the origin or the pole, then it will end up in our third quadrant. So to get our reflected point, we could change the direction of r, maintaining theta, so we could have negative r theta, which will give us the reflected point. Or we could keep r and at 180 degrees or pi to theta to take it all the way around here. So our two alternatives for the reflected point around the pole would be negative r and theta, or r and pi plus theta. So to test for symmetry with respect to the origin, we're going to replace r theta with negative r theta, or with r and pi plus theta. Now we're going to look at a couple of examples that demonstrate the test for all three types of symmetry. In this example, we're going to test for symmetry with respect to the line theta is equal to pi over 2, the polar axis, and the pole. Our polar equation is r is equal to 9 cosine of 3 theta. If you recall, to test for symmetry with respect to the line theta is equal to pi over 2, we can replace r and theta with negative r and negative theta. So by replacing r with negative r and theta with negative theta, we get negative r is equal to 9 cosine of 3 times negative theta. 3 times negative theta is negative 3 theta. We know the cosine of an angle is an even function, so cosine of negative 3 theta is the same thing as a cosine of 3 theta. However, we still have negative r, so by replacing r with negative r and theta with negative theta, we get negative r is equal to 9 cosine of 3 theta. So we know this is not symmetrical with around the line theta is equal to pi over 2. If it's symmetrical, then both equations should be the same. So here, this is not symmetrical. Let's test the polar axis. For polar axis, we're going to replace r theta with r and negative theta. So we still have r, and we're going to replace theta with negative theta, so this becomes 3 times negative theta. So for the same reason, this becomes 3 theta, since this is an even function. So here, this is equivalent or the same as the original function, so we know it's symmetrical with respect to the polar axis. To test for the pole, we're going to replace r and theta with negative r and theta, which gives us negative r is equal to 9 cosine of 3 theta. We can see that this is not equivalent to this, so it's not symmetrical around the pole. Furthermore, we know this was symmetrical to begin with, since this is a function of cosine, and we know cosine functions are symmetrical around the polar axis. So instead of doing all this, we knew from the very beginning that this was symmetrical with respect to the polar axis. In this example, we're once again testing for symmetry around the line theta is equal to pi over 2, the polar axis on the pole. Our polar equation here is r is equal to 2 over 1 plus sine theta. To test for symmetry around the line theta is equal to pi over 2, we can replace r with negative r and theta with negative theta. If we do that in this problem, we'll see that it does not produce an equivalent equation. We can however try our alternative to test for symmetry around theta is equal to pi over 2, which is r and pi minus theta. So we're going to keep r and replace theta with pi minus theta. So now we have r is equal to 2 over 1 plus sine of pi minus theta. If we use our identity for the difference of signs and expand this, we get 2 over 1 plus sine pi cosine theta minus the cosine of pi times the sine of theta. We know that a sine of pi is equal to 0, so 0 times cosine theta will eliminate this. We know that a cosine of pi is negative 1, so the negative 1 will make this a plus 1, so plus 1 times sine theta is positive sine theta. Here we can see that this is equivalent to the original problem, so we know it's symmetrical around theta is equal to pi over 2. Furthermore, this function here is a sine function. We know when r is written in terms of a sine function, it should be symmetrical around the line theta is equal to pi over 2. To test for our polar axis, we can replace r, we keep r and replace theta with negative theta. So we have r is equal to 2 over 1 plus sine of negative theta. We know this is an odd function, so this becomes negative sine theta. So this is not equivalent, so we know this is not symmetrical with respect to the polar axis. Here for the pole, we can replace r with negative r and we keep theta. Once again, this is not equivalent to the original equation, so it's not symmetrical. So only the ones that are equivalent are symmetrical. So here, this graph is symmetrical around the line theta is equal to pi over 2 only.